High up in the silent void of space, there's this one particular region that's become a total graveyard for data. It's a massive headache for engineers, a place where our most sophisticated tech just gets, well, zapped by some invisible force. So today, we're diving headfirst into this Bermuda Triangle of space.
And look, this is a really persistent and super costly mystery. We're talking about satellites, the International Space Station, powerful telescopes. They all run into the exact same problem when they fly over this huge patch of the South Atlantic. Their systems start to glitch, their data gets totally corrupted, and sometimes they just power down. So the big question is, what in the world is going on up there?
And I want to be clear, this isn't just some minor inconvenience. We're talking about the legendary Hubble Space Telescope, our main eye on the entire cosmos. It actually has to power down its most sensitive instruments every single time it passes through this zone. It's a scheduled, recurring problem, which just goes to show you how serious this threat really is.
I mean, this is a huge issue. Just to put it into perspective, over the last few decades, the National Geophysical Data Center has logged more than 4,500, that's 4,500, spacecraft anomalies. We're talking glitches, malfunctions, even total failures. And they've all been traced back to this one hazardous radiation environment in low Earth orbit. It's a very real, and believe me, a very, very expensive problem.
Okay, so this mystery finally has a name. The culprit behind all these technological nightmares is a phenomenon called the South Atlantic Anomaly, or as scientists call it, the SAA. And no, it's not some mythical beast, it's a very real feature of our planet.
And whoa, this map really shows you the scale of what we're dealing with. You can see it right there. The SAA is this massive hotspot of intense radiation. It's like a giant invisible bubble stretching all the way from South America almost to the coast of Africa. Seriously, anything in low Earth orbit that flies through that zone gets hit with a dangerous dose of high-energy particles.
So, here's the crucial point. The SAA is basically a dent, a huge dent in Earth's magnetic shield. It's a weak spot where our planet's natural protection is just thinner, and that allows these things called the Van Allen radiation belts, which are just zones of trapped super high-energy particles, to dip way, way closer to the surface than they do anywhere else on the planet.
All right, so to really understand why this weak spot is such a big deal, we kind of need to take a step back and appreciate the shield itself. I mean, what is this magnetic field and where does it even come from?
Okay, so picture this. Deep, deep beneath our feet, we're talking like 3,000 kilometers down. There's a massive ocean of swirling, molten iron. This outer core acts kind of like a giant spinning conductor, like in an old bicycle dynamo. And that motion generates these incredibly powerful electrical currents, which in turn create our planet's magnetic field. It's this geodynamo that powers our invisible shield.
And the effect of that field? It's absolutely profound. It creates these massive structures around our planet that we call the Van Allen radiation belts. And as you can see, they're kind of like these giant donuts of trapped energetic particles that come from the sun and deep space. The magnetic field holds them in place, and that protects us down here on the surface. But for our satellites, flying through them is like flying straight into a storm.
So let's get back to the South Atlantic Anomaly, that spot where those belts dip low. Down there, satellites are totally exposed, and the radiation they run into isn't just one kind of danger. Oh no, it actually attacks their electronics in 3 very distinct ways.
Now, what's really cool is how this breaks down the attack. You've got different particles, electrons, protons, heavy ions, and they all interact with electronics in different ways. And that leads to this trio of really destructive effects. So let's take a look at each one.
Okay, first up, you've got the slow burn. It's called total ionizing dose, and it's where radiation just gradually wears down the components over time. Then, there's displacement damage, which is way more brutal. This is where high-energy particles literally knock atoms out of their crystal structure, causing permanent damage. And finally, you have the most unpredictable threat of all, single-event effects. This is where just one rogue particle hits a critical spot and causes a random, catastrophic glitch, like a bit flip or a total system shutdown. A great way to think of it is death by 1,000 cuts, a sledgehammer, or a sniper's bullet.
Okay, so we have this weak spot in our shield, and it's causing total chaos for our satellites. We get that. But what if the SAA is just a symptom of something much, much bigger? What if it's a clue that our planet's entire magnetic field is in the middle of a massive, dramatic transformation?
And get this anomaly isn't just sitting there. It's not a static thing. As this timeline shows, when scientists look back at historical data, they can see the SAA has been evolving for a while now. What started as just one single weak spot back in the 1800s has now split and grown.
The African part is actually getting stronger and drifting west, while the American part seems to be weakening a bit. It is a totally dynamic, constantly shifting anomaly.
And it turns out this change is actually part of a much bigger global trend. The main simple part of our magnetic field, what scientists call the dipole, which acts like a basic bar magnet with a clear north and south, well, that part is decaying at a pretty alarming rate. We're talking about 12% per century. But at the exact same time, the more complex, messy parts of the field are surging by 70%. So our shield isn't just getting weaker, it's getting a whole lot more complicated.
So, does all this mean our magnetic poles are about to flip? This is the million-dollar question. The evidence is, well, it's tantalizing, but it's not a slam dunk. On one hand, the rate of decay totally matches what we've seen before past reversals. And statistically, you could argue we're overdue for one. But on the other hand, the field's overall strength is still within the normal range for, the last 780,000 years. It's a massive scientific debate, and the South Atlantic Anomaly is Exhibit A.
And now we can actually trace the SSA's origin right back to the source, the edge of that liquid outer core we talked about. Deep, deep down below the South Atlantic, there are these really strange patches where the magnetic field is literally flowing in the wrong direction. It has reversed polarity. And it's the growth of these specific patches that's creating the weak spot we're seeing up here on the surface.
And all of this brings us to our final and maybe most critical question. The key takeaway here is that this huge problem for our technology in orbit, it's also a totally unique window into the churning heart of our planet. The SAA is like a giant warning sign that our protective shield is in flux. So if it's not a full reversal, then what does happen next? Well, that is the mystery that scientists are racing to solve.